right, so our next speaker is Beck, talking about model-based approaches to multi-attribute diverse matching.
Testing, is this coming? All right, good. All right, so thank you. It's nice to be back at a conference in person. So I'm going to talk about multi-attribute diverse matching. And so I'll start with weighted bipart matching. In fact, I'll start with bipartite matching, which most of you know about. So we've got two sets. We need to match items from one side to items to the other side. Bipartite B matching, we have one of these sets where there's B elements, in this case, on the right side that has to be matched to each element on the left side. So that's where the B comes from. And then we add weights, and we're looking at minimizing or maximizing the weights of the matching. So we have both B matchings required and a weight function. What we're going to do following previous work is add diversity to this, so that we're not simply interested in minimizing the weight, but we also want to combine this with some measure of diversity over multiple factors. That is, the teams that we're assembling need to have some levels of diversity. Motivations for this, a number of them: team formation. There's been cognitive studies that look at the creativity that comes out of the team coming from diverse backgrounds. Things like paper reviews. Obviously, if you're submitting a paper to CPAIOR and it's a MIT paper and you get all CP reviewers, that's not very useful because they'll kill it. And indeed, recommender systems where the group of items that are used to recommend something, the group of records, some diversity in there will help with the overfitting. So multi-attribute diverse weighted bipartite B matching. Okay, and this is from a paper in IJCAI 2020 by previous authors. Diverse matching, we want to reward diversity in each team, and we want to do so in more than one feature. So in this example here, we've got two features, and I'm looking at the different colors as the different indications of the values of those features. And with the matching we have here, you can see that the teams are non-diverse. The first matching is completely non-diverse. The second one is diverse in one feature, but not in the other. If we flip the middle two, okay, so the third one down gets assigned to the top one, okay, we can achieve a better diversity, okay, but in this case, there's no way to actually achieve full diversity because there's always going to be one value of one feature that matches regardless of the way that we do the matching. And so the idea is we want to maximize this measure of diversity combined with the weight function. And there's been a bunch of work on what the diversity function should be. Okay, people have settled on supermodular functions so that the less diverse it is, the more and more it costs. Again, this is from the IJCAI paper. And just to run you through that, it's a quadratic function, right? So here we have one feature, blue and purple, and we've got a cost here. So I'm flipping it around. This is similarity, which is because I want to minimize weight, I also want to minimize similarity. And here we have a similarity measure of 4 when there's a match there. And here we have the minimum similarity of 2 when we actually do get a difference in that feature. Okay, so again, we're still working on previous work here. The standard multi-MD WBM. We have this multi-attribute similarity. We have the weighted assignment. And what we're trying to do is we have degree constraints. So each team U has exactly DU workers. So I'm going to kind of talk in this team to worker assignment context. And each worker V can be assigned to at most one team. And so previous work from IJCAI, unfortunately, has some flaws in it. So this was the paper that introduced the problem. And our motivation for doing this originally was we were looking at solving quadratic unconstrained binary optimization problems. And this looked like a great problem for us. Unfortunately, we discovered that the MIQP model that was proposed in the IJCAI paper actually formulates a relaxation of the problem. The decision variable is this number of workers whose feature F value is GF on a given team. There's no actual variable that does the team to worker assignment. As a consequence, you can essentially do something like this, where even though you have a matching, you can kind of, because there's no representation of that matching, you can get a super optimal solution, okay? They also suggested a local exchange algorithm, which they proved was going to always find the optimal solution. Unfortunately, we have a counterexample that shows that it gets stuck in a local optima. And so what this paper is about then is reconsidering this problem. We want to come up with some model-based approaches to solve this problem, and we want to investigate QUBO models to solve this problem. We also add constraints. Okay, so there's a number of practical constraints that we observe in similar problems in the real world that we wanted to add. And in fact, the one big advantage of the model-based approach is that in many cases, we can just add them very easily. So a conflict constraint, which says these two workers can't be on the same team because they've got some personality conflict. A binding constraint, which says these two workers must be on the same team, could be any team. A conflict assignment, which says this worker cannot be on this specific team. So in this case, we're in a situation where the teams are not just groups of people. Perhaps this is a paper evaluation, a peer review. And so obviously somebody with a conflict with that paper can't be assigned to the team that is doing that paper. Binding assignment is the reverse. This person must be on this team. This is the expert in this area. And so we want to have this person review this paper. A must-have, so in this case, every team must have a person with a particular feature value. So in an engineering project with students, maybe we want to have somebody who knows how to program on every team that we're actually trying to assemble. And the third one, a final one, is a not alone constraint, which says for a given feature value, we either want to have 0 people with that value on the team, or we want to have more than E. So for example, again, in the context of assembling engineering teams in student engineering teams, it's often the case, or sometimes the case, that we want to make sure there's either 0 women or more than 2 on one of these teams. It helps with the dynamics. Okay, and so this is a pretty straightforward model. So the binary quadratic programming model, we've got XUV, which is 1 if worker V is assigned to team U. We've got the diversity, or actually the similarity measure that we're going to optimize combined with the weighted measure. And we have 2 constraints, which is the degree constraint and making sure that each worker is assigned to exactly 1 team. And we add a dummy team that doesn't have the degree constraint on it. That'll suck up everybody else if there's more workers than can be assigned. So this is really straightforward. And I'm not going to go into detail with these ones. We can pretty much see that they're pretty easy to do. A lot of these are just assignments ahead of time. The only slightly interesting one is the not alone constraint, where we just have to make sure that it's either 0 or greater than or equal to E based on a parameter. All right, so QUBO. So QUBO is quadratic unconstrained binary optimization. And the reason we're interested in this is there's a lot of custom hardware that solves such problems these days. So both quantum hardware, so D-Wave's quantum annealer, as well as a number of companies that have developed classical chips that in hardware will solve QUBOs. So part of this is the end of Moore's law for general purpose processors. And so a lot of these companies have thought, given what goes on with GPUs and machine learning, can I construct a chip that does something very well? Okay, and we're going to actually work with the Fujitsu digital annealer. It's completely classical. Unfortunately, some of the marketing literature talks about quantum-inspired stuff. It's not really quantum-inspired, except that it solved QUBOs. It's massively parallel simulated annealing. Some really interesting work on different temperatures at the same time that are exchanged between these replicas, and some extra stuff for one-hot acceleration, because the one-hot constraint is something that comes up again and again in these models. Okay, and this is the form, the general form, right? So we have quadratic. So these are all 0, 1 variables, a weighted quadratic. We have the bias individual, and in general, we also have a constant, but obviously doesn't matter for optimization. And everything is in the objective function. If we have a BQP, it's almost always really easy to turn it into a QUBO. We just stick all the constraints into our objective function and penalize them appropriately. And so our degree constraint and our assignment constraint go in exactly as you expect them. Okay, and the objective function was already a cubo. And so this was one of the reasons we wanted to solve this problem in the first case. And I'm not going to go into it, but the other constraints from the BQP can be added directly in exactly the same way. Okay, so we've got a couple of CP models. An assignment model, we have XV if worker V is assigned to team U. So we're going to index the teams. And the usual definition that I've been using so far, CUFGF, which is the number of workers assigned to a team U having GF per feature F. Okay, this gets a bit complicated because we're trying to count C and X, or C and X, and make sure they're all connected together. I'm just going to sort of give you the overview of the model. So we have a cardinality constraint for ensuring the degree constraints. We have a knapsack linking the assignments with the counts, which was the error in the original MIQP model. We've got a spread constraint to deal with the standard deviations, to deal with the quadratic. You can actually transform them nicely into a constraint on the variance. And so that goes in nicely. And we've got a few other pieces to calculate the weight, calculate the similarity based on the spread, and the other pieces of our model. Okay. Secondly, we have a selection CP, which uses an ordering over the workers. And so XUK is V, if V is the kth worker assigned to team U. Okay, so we're introducing some symmetry, which is unfortunate. And this gets kind of complicated. We also have to add a value for feature F, so the Z value there. Okay, I'm not going to go deep into the details here, but because of the ordering over the workers, we have an all different. We have a spread again for getting the similarity over the features. And we've got some ugly stuff to kind of link things together, a table constraint and a GCC, which isn't too bad. Okay. And the 6 extra constraints from the constrained part, we can do it fairly straightforward with some counting constraints, nothing too sophisticated. All right, so we're going to look at mean relative error compared to the best known solutions. We've got 2 CP models, which we're going to solve both with CP optimizer. And then we're going to look at Gurobi with the quadratic programming model, so GBQP. And we're going to have 3 different ways to solve the Kubo model. We can put it into Gurobi. We can use the Fujitsu DA3. And this is a classical taboo search for Kubos. So it's specialized for Kubos. This is a multi-start taboo search that's developed by D-Wave. So of course, D-Wave does quantum computing, but they also have a taboo search. So this is not quantum computing. This is a classical taboo search. Okay, so this is a paper review data set. This was the one that was originally used in that was used in that IJCAI paper. So what we have is U is the number of papers, V is the number of reviewers. We only have 2 features. One of them is they've clustered all of the reviewers, all the papers and all the reviewers essentially into 5 categories. So it was originally, I think, 25-dimensional. They did a clustering into 5 different categories. And so one feature has 5 categories. Unfortunately, and I think this is a problem with this data set, they then took that, doubled the people. So you have exactly the same set of people and flipped their gender. And so you have a male and a female with exactly the same values in that other feature. So this obviously introduces some unfortunate structure. And I don't think this is a great problem set. In any case, okay, all the exact methods except Gurobi on the Kubo model find and prove optimality. Okay, the Kubo model, memory's out. That's not terribly surprising to me. If you've got a constrained model and you want to solve it with Gurobi, you want to represent the constraints, right? DA3 and taboo search. DA3 also finds, but obviously doesn't prove optimality on all these instances. And the taboo search also times out. The more interesting thing is this work over time, where you can see DA3 very quickly finds the optimal solutions. The other ones eventually get down with a bit of an advantage of, I think this is CP here, right, over Gurobi. And there's not a huge difference between the two CP models in this case. So because of the flaws in these problem instances and because of the small size, we generated some other instances. Okay, so now we've got feature classes, 10 to 100 different classes of features. Each of these classes has between 2 and 10 different values. So we've massively expanded. Microphones has died. I don't know if you can, if you have extra batteries.
Yes.
So what we've done is massively expanded the feature space. Okay, this is the number of binary variables that are in the QO model. And what we're doing here is we're looking at mean relative error. And you can see DA3 finds the best solution we've found on all of these. the CP models are okay. The Gurobi QP in this case times out, our memory's out, right? But the QO model actually does a little bit better, which is a bit weird. And the Tabu search, yeah, it's okay. And so the picture here, interestingly, we've got the QO models are actually all better, so down here, than the non-QO models. And DA3 is actually performing the best. Okay. Finally, we added some constraints. It's not a full experiment on the constraints. We added a number of different constraint patterns. And what we can see here is things are flipped. Now, again, we have DA3 best. We have Gurobi QP the second best. And the non-constrained techniques, right, aren't performing as well as the constrained. Okay. So a bit of a different pattern depending on the problem sets we look at. But overall, the problem can be nicely solved as a QBO with DA3. So our goal was to develop some model-based approaches to this problem, since we thought it was an interesting problem and the work in the literature wasn't enough. The specialized QBO model, with specialized hardware, results in the state-of-the-art results here. And a more general comment is we've been working on QBO models for about 3 years now. It's really hard, despite that it's a hardware accelerated, customized, to actually get QBO models that compete with the state-of-the-art. So I've got a paper at ICAPS tomorrow, actually, that's finally getting some scheduling problems that are close to what CP can do, albeit in a hybrid with CP. So that's kind of not a great victory for the QBO models. But there's an awful lot of stuff in there. I think it's important for our community to understand how these hardware accelerated chips are going to be used to solve optimization problems. And it's not clear to me how to get them to work. I think it works here because really this matching problem is a QBO. And so it's perfect, but pushing it a little bit further, we have problems with doing this. Thank you.
So they're reduced by penalized constraints. Is it possible to do an actual reduction in a classical and hard sense where you actually find new variables? Because it's an hard problem, right? So is there are other kinds of reductions that can be exploited?
Not to my knowledge. I haven't seen anybody trying to do that. I do have somebody working on sort of some reformulations, but that's more sort of on the convexification ways to even take a non-convex QBO and turn it into a convex QBO. I'm not sure it's going to make any difference for these solvers, these customized solvers, because they're not doing any continuous stuff, but it could certainly help other solvers. But I hadn't thought about that suggestion of a more fundamental reformulation, and it might be an interesting thing to look at.
What are the kind of limitations on these diesel chips? I mean, is it similar to the, let's say, D-Wave, where you've got a fixed number of bits and fixed structure that you have to map into?
So the first yes, the second no.
Okay.
So these bits are fully connected. So when you're looking at the quantum hardware, you actually need a physical connection between the qubits, and it's not a complete graph. They've got some specialized graphs. And so when you have a QUBO model, you then have to do an embedding onto this graph. Sometimes you have to use multiple physical qubits to represent a single logical qubit to get the connectivity correct. So in this case, I think the current version we have of the Fujitsu is 100,000 bits fully connected. And in many cases, with smaller problems, we can actually put multiple problems there because it doesn't care that this piece isn't connected with that piece, right? And so sometimes we can actually get multiple levels of parallelism if we can fit it onto the chip.
Other questions? Okay, then, thanks for speaking again.